Good morning to all of you. In this problem, I would like to demonstrate the simulation of another flash column. The previous demonstration, a simple flash column with 5 different types of input options has been demonstrated. I would like to consider a typical problem for the understanding of all the students with respect to the operation of a flash column. This is shown below in the following figure, so I'll discuss about the details slightly later. Now you are required to simulate this flash column and calculate the compositions of the overhead stream as well as the bottom stream for 3 different cases. In addition to this, you are required to modify one case in order to determine the flash temperature necessary to obtain 850 lb per hour of overhead vapor. So this is the process. So you have about 6 components. The mass flow rate, temperature and pressure at which the feed is coming in is already given to you. So in addition to this, now the temperature and pressure at which the flash column is operating is also specified. So given the input, temperature and pressure, we should be able to simulate the flash column and calculate what is the amount of vapor and what is the amount of liquid along with their compositions. This may not be a big deal. However, we would like to analyze what would happen in case if you try to recycle the bottom product back to the flash column. So there are 3 possible cases. One case is there is no recycle. The second case is 25% of the liquid product is sent back as recycle, and in the first case 50% is recycled as bottom product is recycled back to the flash column. So in addition to solving these 3 cases, we also need to calculate the temperature at which the flash column must operate in order to obtain 850 lb per hour of overhead vapor. So the moment you want to consider this problem, you can solve it in 2 or 3 different ways. We already know what is the total amount of feed, and we wanted to get 850 lb per hour of overhead vapor. So calculate 850 by the total flow rate. So that will give you the fraction of vapor that we are interested in generating. We already know the pressure of the flash column. We wanted to calculate the temperature. So you can specify the pressure and probably the vapor fraction based on the ratio of what is the amount of vapor required to the amount of feed. So vapor V by F, in other words V by F, right? So once you do this, then we should be in a position to calculate the temperature at which the flash column must operate. Other words, you can think of using maybe a design specification, keep on varying the flash column temperature until and unless you get a total flow rate of 850 lb per hour in the overhead. So either of these 2 ways you can think of doing. Now in this problem, of course, we are going to even consider these 3 cases. So let us go back and try to solve this problem in Aspen. So you can declare all the components that are involved in this problem. So we have methane. Let me put both these into different windows so that we don't have to. So methane, then ethane, propane, N-butane, then 1-butene, then 1,3-butadiene. So we have defined all the components involved in the problem. So the next step is choosing a property model. I think you have been already given that you are required to use Redlich-Kwong survey option. So let us select that property method. So after selecting the property model, you can go to the next input step, probably go into the simulation environment, create your flow sheet. So I'll try to plan for all these options. So because the feed has to be mixed with the recycle, then we need to go to the flash column. So let me use a mixer to start with. I'm not addressing the valve and other pump and other things because we may not be really interested in energy balance as far as this problem is concerned. But if you are interested in looking at, you can also include these two models, valve as well as pump. So once the mixed feed, the fresh feed with the recycle is mixed and it is going to be sent into the flash column. Now, again, at the bottom, as you can see from this, at the bottom, product is to be split up into two parts. One stream is taken as product, the other one is recycled. So in order to accommodate this, I will also be using a splitter. Right. So these are the three models that we are going to have as far as this problem is concerned. So let us try to connect inputs and outputs. So the combined feed is entering into the flash column and the top product is withdrawn as a vapor product. The bottom product is sent into a splitter and this is further divided into two parts. One stream is taken as product, the other stream is sent back in the form of a recycle. Of course, you may have to pump, which I am not using as far as this simulation is concerned. If you are interested, you can add those details. Now, once again, you will be able to see we may have to provide the necessary inputs after simulating this model. So let me go into the next input. Now the feed is entering at a temperature of 85 degrees centigrade and 100 psi because most of the data pertains to, I'll change the unit system to engineering. So the temperature is 85 degrees centigrade and the pressure is 100 psia. And the total mole flow we don't know, but we are given with mass flow. So we can see the mass flow is methane is 50, ethane is 100, then propane is 700, then 870, 1176, then 5130. Right? So we have specified the the input stream. Now we are required to specify the block. No other streams are required to be specified. So go to the next input. Okay. Now we are being asked to represent the conditions within the flash column. We already know the temperature and pressure. So the temperature is 5 degrees centigrade and the pressure is 25 psi. Right. We have specified the flash column. Then go to next. So we need to specify the split fraction. So you can see from the main flow sheet, the product is 5, the recycle is 6. So to start with, let me take up the case 3. I will be assuming that there is no split fraction, or we would like to define the split fraction as 0. That means everything is with respect to the recycle, nothing is being sent into the recycle. Stream 6 is representing the recycle. Stream 5 is representing the product. So initially, I don't want to put anything in the recycle, right? So later, we will be able to calculate what will happen if there is some amount of recycle happening. So once we come to this, then we should be in a position to simulate the problem. So let me run this problem. You can see that the required input is complete. So we should be able to run the problem. Why there were iterations and what is the method that has been used to solve this problem? What do you mean by converging tear streams? We'll come to this part later. So usually, now this is the recycle. Now you can see from the control panel, the order in which the problem is solved is the computational sequence is block B1, B2, B3. This is the order in which the simulation is done. The simulator has decided this particular computational order. How will you be able to solve B1? For example, you have already specified stream 1. Now, in order to solve B1, because B1, which is a mixer, is going to operate in rating mode. So, for any rating problem, we need to know both the input streams. To start with, we did not have any idea about this recycling. So, how is it possible to solve this model to calculate stream 2? So, whenever you have a recycle in sequential modular approach, the recycle is automatically taken as the tail stream. Tail is nothing but guess. So the simulator will be making guesses for this particular stream. So usually what do you mean by guessing a particular stream? At least you are required to guess variables equal to the number of components plus 2. So that you will be in a position to calculate any property with respect to that stream. In other words, you must be able to satisfy the degrees of freedom for that stream, which we have already seen as C plus 2. So initially we know, though until and unless it solves the splitter, it doesn't know that there is no recycle. We deliberately said the recycle is equal to 0 as far as this particular, at this point of time, the simulation is concerned. But until and unless it solves B3, it will not be able to identify that 6 is void in the sense 0. So it will be taking values, guessing values for this state stream. Given the feed stream, guessing values for the tail stream, now it will be able to calculate block 1 to calculate stream 2. Once you know the input to this flash column, you will be able to solve the flash model to calculate stream 3 and stream 4. Now you solve block 3, you will be able to calculate 5 and 6. Now you started with an initial assumption. Now after solving this model, you got to an updated value for this stream 6. Compare whether the assumed values are equivalent to the present values. If not, you start with another guess and repeat this process. So the moment you have a recycle, it is going to be an iterative process. Especially in this case, we know that there is no recycle, so there were no iterations. Only within first iteration, the simulator was able to identify stream 6 does not contain any material flow. So that's why it stopped, and we will probably see when we put some recycle, what will be the number of iterations and so on. Okay. Now let me try to analyze the solution of this problem. You can see, of course, other things. This is what we have given, right? Let me see the mole flows. So stream 3 is the vapor product. Stream 4 is the liquid product coming out from the flash column, right? So you can see the quantities of various components present in either stream 3 or stream 4, and you will also be able to know out of the total number of moles, 153 moles of 1 moles per hour of the total feed, 92 moles of vapor product is obtained and 60 moles of bottom product is obtained. Now we wanted to get this to something like 180 lb per hour. Of course, not lb moles. We will see that also if you want from mass flows. Now you can look at the composition. As you can see, the composition of methane in the top product is about 3%, and similarly ethane 3%. And predominantly you are going to have 1,3-butadiene, and you can see the mole fractions of the bottom product as well. Right? Now looking at the mass flows, a total of 8,026 lb per hour of mass is going into the flash column, and we were able to get roughly more than 50% of that is recovered into the vapor product. Now remember, we are operating this column at a temperature of 5 degrees centigrade. So now in order to get an amount of 180 lb per hour in the top product, what should be this temperature? Now you can analyze and see when the temperature is 5, we were able to get about more than 50% of the vapor product. But if you want to get something like 180, should the temperature be more or less? So that you can analyze. Accordingly, you can think of using maybe a design spec in order to obtain whatever is required. Because as far as this problem statement is concerned, we are supposed to solve modify case 3 in case of no recycle. The amount determine the flash temperature necessary to obtain 850 lb per hour of overhead vapor. So let us try to solve this problem before venturing into the recycle calculations. Now, in order to solve this problem, naturally, we would like to use a design spec, flow sheeting options, new, design spec 1. Okay. What is that you want to obtain? The vapor top flow. We wanted to get something like, how much is this? 850 lb per hour, right? So that is, consider this top flow is going to represent the stream flow rate of vapor product. Stream is 3, this is the vapor product as far as our simulation is concerned, and this is mass flow in lb per hour. So top flow, this name that I have provided here is going to represent the total mass flow of vapor product coming out of the flash column. Now what is that we are interested in? This value should be at 850 lb per hour. Then give some tolerance. So the spec is specified. What is that you are trying to vary? So this is a block variable because we wanted to vary the temperature at which the flash column must operate. So block is the flash, I think it is B2. Flash column is B2. Then variable is the temperature in degrees Fahrenheit. Now at present, as you can see from stream summary, we are operating this at a temperature of 41 degrees Fahrenheit, and it has to be even lower than that in order to reduce the vapor composition. Of course, we don't have any idea about this. So let us make some kind of an assumption. So top flow, then say next, say block variable, what is the limit? Maybe minus 50 to 40, even at 40, the flow rate 41, also the flow rate is more than 850. So I presume that the solution lies somewhere in between. Remember, the temperatures are now being taken in degrees Fahrenheit. Right now we are operating the column at 40, but we need to reduce the temperature in order to reduce the overhead vapor product. So with this background, now let us run the problem with this new design spec. So as you can see, now because of the recycle, there were iterations involving all the 3 blocks, but because of the design spec, there were iterations with respect to block 2, that is the flash column, in order to determine the temperature at which it must operate. You can see for solving a design spec, we are using secant method, and for solving the recycle, we are going to use maybe the Weijstein method. That will be made clear probably when we go into the recycle options. Now you can see when the temperature initially was 31, the flow rate is 1497. Remember, this is mass flow, and when the temperature is brought down to 24.47, it is 850. Right? So the temperature of the flash column, instead of 5 degrees centigrade, you must be in a position to operate that at 24 degrees in order to obtain 850 lbs per hour. Now as you can clearly see, in the case of design spec, what is that we are trying to do? This is the measured, This is the measured variable. We wanted to maintain 850 lb per hour of this vapor product. We started with some temperature within the flash column. So we try to solve this flash column, calculate the flow rate, compare the flow rate with your requirement. If it is not met, you are supposed to assume another temperature for the flash column and repeat this iterative process till you come to a convergent solution. So this is typical in the case of any design specification. So we were able to get to some kind of a result, right? So let me probably close down this or deactivate this problem because we have already solved the part B. Now let me reinitialize and run the problem again. Remember, if you look at the results of this, automatically the flash column would be operating. I think I just reinitiate it. So you will come back to the same results before the design spec. So 41 degrees Fahrenheit, 25 psia, these are the quantities that you are able to get. Now let us go back to the part 1, handling the recycle calculations. Now what is that we are trying to do? Earlier we have assumed that there is no recycle, our entire bottom product is being routed to the product stream. Now I would like to send back 25% of the recycle stream into, 25% of the bottom into the recycle stream. Just before we do this, let me probably look at this stream summary and look at the compositions. What we can do is go to home, say report. What are the components that you are interested in, these streams? I am interested particularly with the streams coming out of the flash column. So they are 3 and 4. Okay. Now you can see stream 3, what is its mole fractions, vapor, at least the flow rates are available, but what I am interested is in mole fractions. Let me deal with this. Just give me 1 minute. Yeah, these are the stream results when we are using no recycle, right? So I would like to compare this composition when we try to put something back in the form of a recycle. So let me probably store this information with the flows. Flows. So I'm just, for convenience, I'm trying to take this part for comparison's sake. So these are some of the results when we did not have any recycle. Okay, let us come back to the problem now. Now, what is that you want to do? So I wanted to send back 25% of the bottom product in the form of a recycle. Right? This is the only change. Now, with this recycle, what will happen? So we got to a convergent solution. Remember, again, we are using wage steam, and there were 3 iterations. And the model, the simulation is required to solve B1, B2, B3 iteratively for at least 3 iterations in order to come to a convergent solution. This is because initially it will be presuming a value for this recycle stream and go on updating it until all these recycle stream values come to a convergent solution, right? Now let us look at the summary. Now, do you expect, what kind of changes do you expect compared to the results that we have obtained when there was no recycle? So these were the results now. Okay. Now, do you expect, sorry, instead of all the results, let us look at only the stream results of flash column. This is what we will be interested in. These are the stream results with respect to the flash column, the input, output, and also, output in the sense both with respect to vapor and bottom products. Would you do some kind of a change in composition, change in flow? What is the effect of this recycle? What do you think will be the effect of this recycle? We already have the previous results. These are the flows and these are the mole fractions. Now let me copy this new data with 25% recycle. Now I think I'll slightly reduce the content size so that you will be able to see both the tables. The first table corresponds to when there is no recycle, and the second table corresponds to the data or results when 25% of the bottom product is recycled back. Now just try to compare the composition of the top product in both cases. Did you see any change? And similarly, do you see any change with respect to its quantity? So there is no change in the quantity, there is no change in its composition. Exactly, you are reproducing the same. And what about the quantities? Even the quantities are one and the same. So the recycling the bottom product, of course 25% of the bottom product back to the flash column is not resulting in any change either with respect to the composition or the quantity of the vapor product that you are generating. Now let us look at the bottom product, which is a liquid. These were the compositions of the bottom product when there was no recycle. Now these are the compositions when there is recycle. 25% of the liquid product is sent back in the form of a recycle. Once again, you can see that the compositions, there is absolutely no change. But with respect to the flows, earlier the amount of bottom product was 30 to 64. So many LB per hour. Now it got increased to 4353 because of the recycling. So the allowing some part of the recycle back to the column from the bottom product is not resulting in any change either with respect to the vapor product composition or bottom product composition. And in fact, the quantity of the top product also is remaining constant irrespective of whether you had recycle or not. Because you are sending the liquid product back to the column, there is an increase in the liquid product when there is some recycle compared to when there is no recycle. Probably you can analyze this problem from theoretical point of view, whether some of these results are going to make sense or not. In the same way, you can also compare what will happen if 50% of this is sent back. So now you are required to select 0.5 here and try to compare the results of what you have got with 0 recycle, 25% recycle and 50% recycle. And the same conclusions you will be able to draw. It will not be affecting the composition of either vapor product or liquid product. The only change that it will be resulting in is increase in the liquid product flow rate. Why is it so? Remember, the bottom product, what are the conditions? 41 and 25. What is the condition of this particular fluid at the bottom? Now it is going to be a saturated liquid with respect to the components at the given temperature and pressure. Now when you are putting it back to the flash column at the same temperature and pressure, automatically, because the temperature and pressure at which the flash column is operating remains constant, the compositions will have to be the same. This is obviously dictated by the vapor liquid equilibrium. Now in the same way, if you are interested, what you can think of doing is, instead of recycling the bottom product, what will happen if you try to recycle the vapor product? Once again, the same results you will be able to conclude that the recycling the bottom product or vapor product will not be affecting the compositions, but the only change would be the quantity that you are trying to recycle. If you are recycling a bottom product, the quantity of the bottom product increases. And if you are trying to recycle the vapor product, the quantity of the vapor product will be increasing. But you will not be able to make any change with respect to the composition, right? Of course, there will be some other changes that you can probably analyze. Now the feed is at 100 degrees centigrade, the bottom product is at 41. Earlier, there is no recycle, but 25% of that is being recycled. Now the output temperature that is entering into the flash column will be different from when there is no recycle. Accordingly, ultimately, we are not changing the temperature and pressure at which the flash column is operating. But if there is some change in this inlet temperature because of the recycle, there will be a change in heat duty. Of course, in the previous case, I did not observe the heat duty. Now you can think of looking at the results. Now, the heat duty is minus. What do you mean by this? Is it added or removed? This is again as per your thermodynamic notation. Any energy added to the system is taken as positive. Any energy removed from the system is taken as negative. So when you are putting 25% of the bottom product into the recycle, you are required to remove this much of heat in order to reduce the temperature, whatever may be the inlet temperature. Of course, you can see this. This is about 106 degrees Fahrenheit. In order to reduce this temperature from 106 to 41, this is the amount of heat duty. Now, naturally, when you put probably 50% of the feed back into the column, now the temperature will be different and the heat duty also will be different. Just have a look at this heat duty so that you can make a comparison. So about, let me convert it into maybe kilowatts, about minus 287 kilowatts, right? Now, when you try to put 50% back, this heat duty will be definitely changing. Now, once again, you can see, and probably you will also be able to see the stream summary, flows and compositions. Once again, you can compare with the previous results and see that the compositions of 3 and 4 will remain the same. Now, earlier, I did not remember the mass flow, but now there is an increase in the mass flow. Whereas the mass flow of the vapor product or mole flow of the vapor product, there is no change, right? That you can see. Let me see this temperature. Earlier, the temperature of the stream was at 106. Now it is 45, right? Because 50% is recycled back, which is at 41, right? So obviously, from this, you will be able to see the heat duty will be reduced. Try to see in kilowatts. Yeah, it will remain the same. Why is it so? More quantity, because earlier the amount of feed entering into the flash column is lower. Now more quantity is getting admitted into the flash column. All that amount should be reduced to 41. So probably this may be by chance, but you can think of analyzing what would be the changes of recycling either the bottom product or the top product back to the column, right? As long as you don't change the temperature and pressure at which the flash column is operating, the temperature and pressure at which the flash column is operating is going to dictate the composition of the vapor product and bottom product. You can probably verify that from your VLG information. So until and unless I change this temperature or pressure or some conditions at which the flash column is operating, I will not be able to bring in any change in the composition. Right now, the recycling of either the bottom product or vapor product is not influencing the temperature and pressure at which the flash column is operating, so the compositions will remain the same. But as you know, from the mass balance, mass is neither created nor destroyed. Whatever mass that is entering should be able to come out. So if you are recycling liquid product, the liquid product quantity will increase. If you are recycling vapor product, the vapor product quantity will be increasing. So I'd like to start this demonstration, stop with this demonstration with this.